Hey there. All right, so we are starting chapter 7, part 2. Okay, and what we're going to begin with today is we're going to begin with the octet rule exceptions. Okay, so a couple of elements, mostly just boron, tend to form compounds where they have fewer octets. They don't actually complete their octets. And the reason for that is, let's take a look at boron. All right, boron is number 5 on the periodic table, and it looks like this. And so if we kind of hold with the idea of paired electrons, then here you can see places where we could have elements, and you can see that there's nothing down here to pair. So sometimes you will get a pair there. For example, boron can make B2H6. Okay, so B2H6 would look like this. And in this case, we have boron meeting the octet. But then we have BH3, so sometimes boron doesn't, especially like if boron is with fluoride or things like that, then it's perfectly happy not filling its octet. All right, and then here with hydrogen. So let's just take a look at this. Okay, so our boron is 3, and we're getting 3 times 1 from the hydrogen, so we have 6 electrons. And so we would say, okay, well, we have boron, and there we go. And we've got 2, 4, 6, and we're done. Okay. Now notice how there's this big gap on top. So I'm going to put in a little something. In just a few minutes, we're going to be learning about VSEPR, V-S-E-P-R, valence shell electron pair repulsion. And there will be tests on how fast you can say that. Anyway, now see this. Now nature likes to be very balanced as opposed and neutral. So in order to show this as balanced, this first one is completely correct for a Lewis structure, but you can see that this would probably be more stable in nature, right? This would be more sturdy. Like you wouldn't necessarily have it look like this with just nothing, this like nothing gap up here. Okay, you wouldn't have this nothing gap up here. And so a lot of times when we have just the 3 things coming off of the center, then we'll draw it like this. All right, now let's take a look at a couple more. We have, oh, I didn't realize that, but there's, if you're looking at your own, you'll see that there's stuff drawn here, but that's okay. I want to draw it anyway. All right, SF4. Okay, now let's take a look at SF4. So our sulfur gives us 6 electrons. And our fluorine, we have 4 of them, so that's 4 times 7 electrons. Okay, so 28 and 6 is 34. So that's where we get that 34. Now, normally you would say, okay, well, but sulfur comes with 6 electrons, so it looks like this. And this is where starting with this kind of a structure sometimes doesn't work, because this only shows you 2 places for bonding. But sulfur is in our 3rd row. And once we get into n equal to 3, here, see, once we get into n equal to 3, we have 3d orbitals. But for every row, for example, sulfur is in 3p4, okay? Sulfur's valence here looks like neon. And then it has 3s2, 3p4. It won't get to the d orbitals next. So it's got all these unused d orbitals. So what sulfur can do is it can put extra bonds in its d orbitals because it's in row 3. Okay, so now in this case, you wouldn't be able to start with this. We have the 4, so we know that we're going to look like this. All right, so we'll start with this. And then we can have So that gives us 8 electrons. Now let's place them around fluorine, because remember, fluorine always has 1 bond and 3 lone pairs. So we're going to do that first. So we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28. Did I count those right? Okay, so we have 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. So one of the things I'm always really, really careful about is that if you're not counting your electrons, you might put these on here and think you're done. And that's why this place where we're counting our electrons is so important. Okay, now let's take a look. We have 32 electrons accounted for, but we have 34 electrons. They have to go somewhere. Okay, and where they're going to go is they're going to go on the sulfur, because fluorine can't expand its octet. All right, now let's take a look at our next one, AsBr5, arsenic pentabromide. Okay, so now arsenic is group 5. It's, well, okay, not with the new IUPACs, never mind. Arsenic has 5 valence electrons. Okay, so our arsenic has 5 valence electrons, and our bromine has 5 times 7. Okay, so that's 35, and 5 is 40 electrons. Okay, so now again, this one is a little easier to see actually. So arsenic has 5 valence electrons, right? 1, 2, 3, 4, 5. So when arsenic, and actually here, when arsenic expands its octet, usually arsenic is going to form bonds like this, right? Okay, and you're used to seeing that because here we've got our little spaces. Okay, but when arsenic expands its octet, it'll go off of these here. And you could even actually say the same thing about sulfur. Okay, you could say here's sulfur's normal bonding places, but then it could also bond here and here if we needed to. But that's what we did with this, is we built bonding places off of the electrons. But you really have to understand where that can happen. And if it does that, it'll bond off here and leave a lone pair. You would never get one line coming here and one line coming here with radicals. Those aren't, unless radicals are necessary, you always leave things in a pair like I did here with this sulfur. See? Okay, going back to our arsenic pentabromide, then we put in our arsenic and we have 5. So let's go 1, 2, 3, 4, 5. And we'll put in our bromines. And now, right now, it's really just easy to see all around where arsenic now has 10 on it, and it's exceeded its octet. And let's see if it's easy. So we've got 10 electrons here, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, and 40. And so we have all of our lone pair electrons on our bromines, and we don't need to put any on arsenic like we did on sulfur, but count those electrons at the beginning and at the end, because it'll save you from a lot of mistakes. And if you've printed your slides, you already have that written. All right, resonance structures. Resonance structures exist when more than one equivalent Lewis structure can be drawn for a molecule. Okay, and the actual structure is an average of these resonance structures, because the electrons in the double bond can be delocalized, which means, so if something is localized, let me come up here. If something is localized, then it's on one atom. And if something is delocalized, then it can move between atoms. All right, so now let's take a look here. So our nitrate ion, and let me go ahead, I want to show you guys how to draw the nitrate. Okay, so nitrate has 5. Hang on. I still have it. There's all, when you guys get to the point where you're practicing this, you'll see how many different tools you have that you can't see on my screen. All right, nitrate has 5 valence electrons, and there are 3 times 6 for the oxygens. And then this negative sign here means 1 more. So we have 18, 19, 24 valence electrons. Okay, and it's NO3. So I would say, okay, well, let's take a look here what this looks like while we're drawing it. So we have nitrogen, and so you have to put the whole thing in brackets with a 1 up here, because that means it's an ion. So you have to do this whenever you have an ion. Okay, and now let's say, okay, well, let's go ahead and put our lines in for our oxygens. Okay, now I have 2, 4, 6, and I have 24 to place. So let's start working on this. So we'll say 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22. Well, that doesn't work, does it? Okay, so we can't, that, first of all, because, oh wait, 20, 22, 24, there we go. Okay, now the problem with that looks great, except for the fact, because all of the oxygens have 8 electrons around them, but the nitrogen doesn't have 8 electrons around it. So, okay, so what we'll do is we'll move 1 pair in like this and make a double bond. Okay, and that's how you have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 24 electrons total. And again, you can always start with counting them. Don't assume anything about the number of electrons that you're going to have. All right, so we have these, but there was nothing to say that, so with this first one, I drew my double bond here, but I could have brought in a pair of electrons on any of them. I could have brought it in on this one. I could have brought it in on this one. And so you could ask yourself the question, which one is right? And the answer is all of them are right at the same time. And so what we'll end up doing is you draw a line like this between your resonance structures. And what you have is you have this extra, you have these extra electrons, right? Your double bond electrons are moving all the way through. And that's why they're delocalized, because they could be here or here or here. They're not in any one specific place. Okay, so one of the ways that we can determine whether or not a resonance structure is a good resonance structure is with formal charges. Okay, and there are different ways of calculating formal charge, but this is the way that I like to think about it. And this is a little bit different than the way your textbook does it, or other textbooks or most videos. I think it makes it simpler. However, if you find another method, you can use that one. So when we're doing this formal charges, we take, here we have the number of valence electrons. Actually, hang on. Okay, let's do this here. Okay, so you can see we have 1, 2, 3 chlorines, and each one of these chlorines is chemically equivalent. They all have 1 bond and 6 lone pair electrons. Great. Okay, so because they have 1 bond and 6 lone pair electrons. Okay, so let's go ahead and take a look at how this will work. The chlorines here are all the same, right? So we only have to do one of them. So if you had them looking different, then you would have to do it twice. Like if you had a single bond to an oxygen and a double bond to an oxygen, they would have different formal charges. So chlorine has, first we have the number of valence electrons of the unbonded atom. So chlorine has 7 valence electrons. And then we have the number of bonds on the atom. So minus 1 bond on the chlorine, and minus the number of lone pair electrons, 2, 4, 6, minus 6. Okay, so in that way, we end up with a formal charge of 0 for each one of our chlorines. And a formal charge of 0 is perfect. It's exactly what you're looking for. Okay, so now let's take a look at the oxygen. We'll do the oxygen here. So oxygen comes with 6 valence electrons. This oxygen has 1 bond on it, okay, minus 6 lone pair electrons, and that gives it a formal charge of -1. And we have the phosphorus down here then. There we go. Phosphorus comes with 5 valence electrons, minus 1, 2, 3, 4 bonds, minus 0 lone pair electrons, and that gives it a formal charge of +1. All right, now our -1 and our +1 cancel each other out, okay, for an overall charge of 0. All right, so now we have molecular structure, VSEPR, valence shell electron pair repulsion. And what that means is that in an atom, every place, or in a molecule, all of these bonded atoms, okay, or lone pairs, like these paddles are lone pairs, okay, they're all pushing away from each other to repel each other. And so the geometry is designed to have the maximum bond angle possible for every electron. So there are 2 possible geometries for every molecule. There's the geometry of the electron arrangement, or the electron arrangement geometry, the electron arrangement structure. It's called different things. And the other one is the geometry, shape, or structure of the molecule itself. And in this one, you kind of ignore that. So these are the same, okay? These are the same if there are no lone pairs on the central atom. But they are different if there are lone pairs on the central atom. So that's what we're going to be looking at next. All right, so first of all, let's look at VSEPR when there are no lone pairs on the central atom. Okay, so I have an example of that. I don't know if you can see that here, but there we go. So you can see this little molecule that I have here. This one is linear. Okay, and you can tell that because the farthest they can get from each other is 180 degrees. So we've got beryllium chloride here as an example. And here's another example of no lone pairs and linear. And this picture here looks like carbon dioxide, okay? And you can see the double bonds there. And again, linear because there's no lone pairs on that central atom. Now, the next one that we have is trigonal planar. Okay, so there's the first one. And you're going to need to know a variety of things. You're going to need to know what this is, and your bond angle. So you have to know each one. So 3 bonds on the center atom is trigonal planar with a bond angle of 120 degrees. Now, sometimes people have trouble with those pronunciations. Trigonal planar, okay? And it would look sort of like this. You can see the model, and then you can see, I don't even know if you guys can see this very well in that tiny screen that I have there. When you do the lab for this chapter, whether you do it in person in the lab or whether you're looking at it in the videos, you will get a lot of practice with this, and the lab really helps cement these concepts. Okay, the next thing that we have is 4 bonds on our central atom, and one of those could be methane. And here is an example of what that looks like. And I've actually used different molecular modeling kits on purpose, just so that you can see the different types. Okay, this forms a tetrahedron. A tetrahedron is a 4-sided geometric object where the sides are all the same, okay? And that's what, so you have 4 bonds, and that forms a tetrahedron, and our bond angle of 109.5 degrees. Now let's take a look at a couple of expanded octets. And remember, we're still working with molecules or ions where there are no lone pairs on the central atom. Okay, the first one here is is 5 bonds on our center atom. See, sort of like this PCl5. Okay, and it's a trigonal bipyramid. And its bond angles are 120 degrees and 90 degrees. And that's because here you can see this triangle here. And so from here to here, you have 120 degrees. And then from this one down to this one, it's 90 degrees. And then, so I'll kind of, there we go, 120. So, and there we go. And this is an example of that. And you can see, if I can line it up, you can see that triangle there and the 2 atoms coming out in the plane of the paper. So you can see in this triangle from here to here, or from here to here, it's 120 degrees. And then if we turn it over like this so that the triangle's on its side, you can see that this one to this one, or this one to this one is 90 degrees, okay? Trigonal bipyramid. Now the next one that we have here is 6 bonds on our center atom, and that's octahedral. And it's an octahedron because, as you can see here, there are going to be 4 sides and 4 sides. So this would make an 8-sided diamond structure, or a octahedral. All the bond angles in here are 90 degrees, and it's hard to see that here, but here you can see 90 degrees. Or from here to here, 90 degrees. So between any 2 adjacent ones, it's 90 degrees. You could also say 180 degrees like this, but those aren't adjacent. And here's an example of that. And you can see, if I turn it over, you can see that square there in the middle. And then if you turn it up like this, you can see the square in the middle and the ones that are coming down like so. Okay, so this is just a review of the previous slides with the ball and stick models that I had. When you do the lab for this, I'll encourage you to have this handy. Okay, now what this one is doing, this is also just, I've got a lot of extra stuff in here. This is also just a quick reference for some options for no lone pairs on the center atom, and it takes you through everything. I would have these handy when you take your tests. Okay, now let's take a look at what happens when we have lone pairs on the central atom. So we still have a tetrahedral electron arrangement, 4 sets on a center atom, but in some cases it's a lone pair. So in this first one, in ammonia, we have NH3 and we have a lone pair of electrons up here. And I'm going to draw the electrons in the paddle. Okay, so what happens, there we go. Okay, so what happens is we have the tetrahedral structure. We have 4 things coming off of the atom, but this lone pair is right here. Now, the lone pair takes up space, but there's not actually something there. So you can imagine it without the lone pair. And there you have a picture of ammonia without the lone pair. So what that means is that when you take the lone pairs into account, you have a tetrahedral electron arrangement, but your shape is trigonal pyramid. Okay, so far I've told you about trigonal planar, trigonal bipyramid, and trigonal pyramid. Make sure that you know the difference. That's really, really important. If something needs to be a trigonal pyramid and you tell me it's trigonal planar, you will be wrong. You won't be half right, you'll just be wrong, because there's a really big difference between trigonal planar, which is right here, and trigonal pyramid, which is right here. See how different they are? Okay, bond angles, everything is different kind of molecule. Trigonal planar, trigonal pyramid. So there's no partial credit on these. You get them right or you get them wrong. Okay, so the next part of the tetrahedral electron arrangement we have is something like with water, where you have 2 bonds and 2 lone pairs. Okay, so we'll say we'll call this a lone pair and this one a lone pair. Okay. And then you have this shape here. And without the lone pair, so it's still tetrahedral without the lone pairs, you have this kind of a shape. Here we go. And it sort of looks like this. Again, different kinds of petals, different kinds of structure. And this is either called bent or V-shaped. I don't usually see V-shaped, I usually see bent, but either one is considered to be accurate. Usually on a test, I'll tell you what I'm looking for, okay? All right, now again, we're dealing with VSEPR and lone pairs on our central atom. So let's take a trigonal bipyramid or a trigonal bipyramidal electron domain geometry. That's a mouthful, okay? And you can see 1, 2, 3, 4, 5. And this graphic shows your bond angles really, really well. Now, if we have, so we have 5 electron domains. Okay, so this first one, okay, we have the trigonal bipyramid here, and this was with no lone pairs. Now, if you replace one of them with a lone pair, then you have what's called seesaw. All right, and seesaw is like this, okay, and you can see the lone pair always goes on one of those side ones. And the reason it's considered seesaw, let me see if I can raise, there we go. All right, let me see if I can try to make it nice and easy to see. Look, so if you've ever gone to a playground and played on a teeter-totter or a seesaw, you can see that it does this. It's like seesaw or a children's teeter-totter. Okay. All right, and then here we have in this one, you can see that we've replaced 2 of them, okay? And that would be the molecular geometry, again, all still trigonal bipyramidal electron domain geometry, okay? But this is our shape, and I might say shape here, because sometimes we'll just refer to it as shape. Okay, seesaw, this one is T-shaped, and I don't have a model for that. Nope. I don't have a model for that, but you can see how it would work. And then in our next one here, we have replaced each one of these with lone pairs, okay? And our shape is linear. And this is like triiodine. Weird, huh? I3. Okay, now we have, again, lone pairs on our center atom, and this is for our octahedral electron domain geometry. Oh, and I can see I need a little space in there. Octahedral electron domain geometry, and here it shows you with all the lone pairs where those are. There are 6 electron domains for octahedral. Okay, and the options that you usually see for octahedral, first of all, when you have no lone pairs, your electron arrangement and your geometry or your shape match. Okay, now if you replace one of these, usually you replace it here, and it makes what's called a square pyramid. And I don't have an example of my square pyramid, but you could sort of see how that would work because this one's empty and now you're, okay, you can see this pyramid and this one's drawn sort of upside down, but it's a square pyramid. And then if you are to replace 2 of them with lone pairs, then you end up with this perfect square. And this one is square planar, okay? And it'll look sort of like this. You can see the paddles here and here, and you can see that the square, it forms a square. All right, and that is the end of lecture. I want to toss one more thing out. You should have seen this in there. If you are taking this as an in-person class, part of your reading comprehension quizzes will be done in class, and it'll be these practice problems that we'll be drawing for this. And that's just because that's what I want you to be practicing for those chapters. If you are taking this with me as an online class, the 5 points towards your reading comprehension will be attending one of the Zoom sessions where we practice this. Okay, and I will ask you, you don't necessarily have to have your camera on, but you do have to have your microphone on so that you can share your screen. All right, I will not be recording it. If you don't want to do it with a group, that's fine, but it's best, then you'll be coming and everybody will be practicing these together where we draw them. And the reason for that is that the test for chapter 7 will have a live component to it, even if you're taking the class with me online. Okay, and I will have let you know that at the beginning of the semester, but a large portion of your test, almost a quarter of your test for the chapter 7 test, is a one-on-one session with me where we will be doing the most important things for chapter 7, and coming to the Zoom sessions will let you know how that's going to work. It's very simple. Most of the time students earn full points on it as long as they have done some preparation. And it's my way, because it's an online class, of leading you through drawing some of this complicated geometry that it's just not possible to do in an online test. It's not possible to ask these ideal questions using an online platform. Your camera will not have to be on, but your microphone will. It's not scary at all. Students are always, the first thing they always say when I'm like, you're done, is, wow, that wasn't that bad, and I just got full points. So it's not scary, but please let me know right away if there's an issue with that. And I look forward to seeing you and drawing Lewis dot structures.